Lesson 41 on power. It's a pretty short lesson. And power is very simply the rate at which work is done. Okay, so a rate is always something over time, just like velocity is the rate at which a displacement is being covered or a distance is being covered. So velocity is a rate also. Power is a rate. It's how much work is being done over a specific amount of time. In this case, it's usually 1 second. How much work is being done per second? And so the units for power are measured in watts after famous English physicist James Watt. And what are watts? They are simply joules per second. Here's the formula for power. Power equals work over time or change in energy over time, because we know from previous lessons that work equals the change in energy. And so it says power is really how fast you are using up energy. It could be measured in, so it can be measured in joules per second. And here's your classic example. I left a 150-watt bulb on for 2.5 hours to determine how much electricity I used. So what are they asking for in that question? They give you 150 watts is the power. So they give you P, and they give you the time that it was on, 2.5 hours, which we're going to have to convert to seconds. And they want you, it says, determine how much electricity I used. They're asking for how much energy or how much work. Okay, so we could put delta E, or we could just put W. W equals PT. So we're just going to multiply 150 times 2.5 times 3,600, because there are 3,600 seconds in 1 hour, or times 60 times 60, whichever way you want to do it. And that's going to spit out a number 1.4 times 10 to the 6. Joules. So which should leave you a little shocked. You should be saying, oh, 150-watt bulb on for 2.5 hours uses 1.4 million joules of energy. Ooh, turn your lights off, or don't use 150-watt bulbs. You should never have to use 150-watt bulb anyway. Second part of this lesson goes on to discuss an interesting derived formula. And it says in many questions, we need to look at situations where a motor is lifting something at a constant velocity. Constant velocity. And we know whenever there's a constant velocity, the only formula that applies is V equals D over T. The difference between motors is that a higher power motor will be able to move the load faster. If we see this, so we can see this if we start to play with the formula a bit. So you can see what they've got here is they've taken work, and we know that work equals force times distance, and they've replaced that with force times distance. But then we notice that we have, right here, we have a distance over time. And so we can replace the distance over time with velocity, and that's how this we get this derived formula. The power equals force times V, but it has to be where something is moving at a constant velocity, because then this formula applies, this formula and that formula only. So example number 2 is actually a little tricky of an example. A 200-watt motor is being used to lift shingles at a constant velocity to the rooftop. If one pack of shingles has 28 kilogram mass, determine the velocity that the pack will be raised. So you got to think about this question in terms of, so we got a pack, it's attached to some string here, and the string's pulling it up there. What's it pulling it up against? obviously gravity. So we have an applied force pulling it up. We have a gravitational force pulling it down, and therefore, that's an A, right, by the way. And therefore, the net force equals the applied force plus the gravitational force. So this is great. We're back into dynamics and net force problems. They will come back at any given point. Net force equations. And what are we trying to determine here? Well, this is why this is a tricky question. You got to think about some things. One, it's moving at a constant velocity. If it's moving at a constant velocity, what is the net force? 0, because there is no acceleration. The net force equals ma, and if a is 0, then the net force is automatically 0. So this is automatically 0. So what we can really say is that the applied force equals the negative Fg, and therefore the applied force equals negative mg. It's 28 kilograms. Negative 28. And here we do need the negative on the 9.81. And that turns out to be 274.68 newtons. So in significant figures, we're going to end up with 2.7 times 10 to the 2 newtons of applied force to lift up the pack. And now, is that what they were asking? No, they weren't asking that. So that's that's the applied force. They're asking for the velocity, and so we can go to that formula which we derived. So this is step 1. Step 2, the formula that we derived was P equals Fv. Therefore, V equals the power over the force. The power in this case is 200 watts. The force, 274.68, and that will give us an answer of 0.73 meters per second, which again seems like a pretty reasonable answer for lifting a pack of shingles. If you get an answer of 20 meters per second, then get the heck out of the way. That's a fast moving pack of shingles. All right, and there ends power.